Okay, ma? So the next concept after work done is specific heat. So already we have defined the specific heat previously, no? In thermal properties only we have studied specific heat. No? What is meant by specific heat? So the amount of heat energy required to raise the temperature of unit mass of a body by unit rise in temperature. That is the meaning of specific heat. No? So if I want to heat a body, one unit body, for example, if you take an SI system, 1 kg of body. In CGS system, 1 gram of body. Clear, Nama? And what is the rise in temperature? Either 1 degree Celsius or 1 Kelvin rise in temperature. Then how much energy you have to supply, that is called as specific heat of a body. Already we have studied this one. So if a specific heat is greater, it means that to raise the temperature of a body, we have to supply more energy, no? If S value is greater, Q value also will be greater. That is the meaning of this one, Nama. So for example, we have studied specific heat of water. How much it is? It is 4,200 joules per kg Kelvin. This is the specific heat of water. Okay, ma? Similarly, if I take a specific heat of metal, lead metal, then it is nearly 130 joules per kg Kelvin. Okay. So if I look at these two values, what do I understand? Can you say? Specific heat of water is 4,200. Specific heat of lead is 130. If you look at these values, what do you understand?
1 kg water needs 4,200.
Yes. So to heat 1 kg of water, so that I raise the temperature by 1 Kelvin, how much energy I have to supply? 4,200. Similarly for lead, metal lead, same 1 kg lead metal, and rise in temperature is also 1 degree, either Celsius or Kelvin. But I have to supply only 130 joules of energy. It means the specific heat of lead is very less. No? It means lead gets heated up very fast. That is the meaning of this one now. So if I am supplying equal energy for both of them, lead metal gets very heated up to a very large temperature very soon, because its specific heat is lesser. Okay. Now we are taking specific heat in terms of mass of the body, Noma. So this type of specific heat is called as gram specific heat. What we call this one, ma? Gram specific heat. What is meant by gram specific heat? So quantity we are taking in terms of mass of the body. Okay, ma? So quantity in terms of what? Quantity in terms of mass of the body, then it is called as gram specific heat. Similarly, we can define one more specific heat which is called S is equals to Q by N delta T. Now what is the difference between this one and this one, ma? This one and this one? Here I am taking in terms of mass, but here I am taking the same specific heat in terms of number of moles of a gas or number of moles of liquid also, anything you can take. Clear? So how many moles of gas we are taking or how many moles of liquid we are taking. Like this also I can measure. So this specific heat I can call it as molar specific heat. Okay, ma? Molar specific heat. So molar specific heat means what? Instead of mass of the body, we are taking number of moles of a gas or number of moles of a substance. Are you able to understand, ma? So gram specific heat, molar specific heat. Don't be confused between these two. Both are one and the same. So here just if you take mass, it is called gram. If you take a number of moles, it is called molar specific heat. Is it clear? Okay. Then we study about specific heat of a gas, ma. Clear? Next concept is specific heat of a gas. Okay. See, ma, gas has one unique property. Ma. Its volume is not fixed. Similarly, its pressure is not fixed. Its size is not fixed. Its shape also, it is not fixed. Gas doesn't have a fixed shape and size, no, ma? Clear, no? So therefore, what I say, gas do not have, or gases do not have a fixed specific heat. Okay, ma? They do not have a fixed specific heat. What is the meaning of this one? For example, if you take water in liquid form, we know specific heat of water is 4,200, no? Fixed value. But gases does not have a fixed value. Okay, ma? So their S value can range from minus infinity to plus infinity. Their specific heats can range from minus infinity to plus infinity. Okay? Are you able to understand what we are writing? S values can range from minus infinity to plus infinity also. It means specific heat can be 0 also, specific heat can be very large also, specific heat can be very less also, depending on how you are heating the gas. Are you able to understand? Specific heat varies from minus infinity to plus infinity. Let us take some examples now so that you can understand how gases can have these many ranges of specific heats. Sima. So, for example, if I take specific heat, S is equals to Q by N delta T, no ma? S is equals to Q by N delta T. Are you able to understand, ma? So, we can rise temperature. We can rise temperature of gas such that Q is equal to 0 and delta T is not 0. Is this possible, ma? This condition, is it possible or not? Once try to answer. Are you able to understand what is happening? So what I want to do here, I want to rise the temperature of a gas. Okay, ma? But I should not supply heat energy. Change in temperature is not 0. It means temperature is definitely increasing. Are you able to understand? Then in this condition, what will be my specific heat? S is equals to 0 by N delta T will become 0, no ma? Is it correct? Why specific heat has become 0? Because Q value has become 0, no? We are raising the temperature, okay? But we are not supplying heat energy. So specific heat has become how much? 0. Now can you say any method how we can heat a gas, how I can rise the temperature of a gas without supplying heat energy? Anybody? Shaking the container. Shaking the container, correct? Still any other method? Open container. We should not heat energy. We should not supply heat energy. Q is 0. But still I need to rise the temperature of the gas. If we compress the gas, that is possible. Clear, ma? See here. For example, this is a container. Are you able to understand? So, molecules of gas are present in this container. Okay. You should not supply any heat energy. Temperature, initial temperature is 30 degrees Celsius. You want to raise it to 40 degrees Celsius. How it is possible? It is possible only if you compress this piston downwards. Okay, ma? If you are pushing the piston downwards, you have to do some work, no, to push the piston downwards. So that work should be converted into some another form. And what is that form? That work which you have done to compress the gas, it converts into internal energy of the gas. So automatically temperature of the gas increases according to law of conservation of energy. Are you able to understand, ma? So work should be converted into some another form. Energy should be converted into some another form. You are doing some work to push the piston, no? That energy which you have spent, it converts into internal energy of the gas. Are you able to understand, ma? So therefore, if I push this piston downwards, what happens? This piston will reach up to here, no ma? Piston will reach up to here. Automatically, temperature of the gas increases. So definitely we are raising the temperature of the gas, no? But are we supplying heat energy? We are not supplying heat energy. But still we are raising the temperature. So in this condition, what is the specific heat? 0. So you can heat the gas such that specific heat is 0 also. Are you able to understand? Okay. Let us see one more method. Okay, ma? So let me take one more case. S is equal to N delta T, no ma? So Q is not 0. Okay. But delta T is equal to 0. Now in this condition, delta T is 0. In this condition, what is the specific heat? Specific heat yanta. Infinity is the specific heat. Why it has become infinity? Because delta T is 0, nama. 0 multiplied by N. 0, anything divided by 0. Infinity. So we are heating the gas such that we can heat a gas like that also. Okay. So in this condition, heat Q by 0 is how much? Infinite. Okay. Now can you say how it is possible that what is meant by Q is not 0? We are supplying heat energy. Q 0 means we are not supplying heat energy. Q is not 0 means you are supplying heat energy. But temperature should not change. How it is possible? You are supplying heat energy, But temperature should not change. How it is possible? How it is possible? Okay, ma? See, first law of thermodynamics we have, na, ma? What is first law of thermodynamics? Q is equals to delta U plus delta W. This is first law of thermodynamics, no? Okay, now see. Are we supplying heat energy? Definitely we are supplying heat energy. What about change in temperature? Change in temperature is not there. It means delta U, if temperature does not change, it means there is no change in internal energy. So delta U also will become 0. It means whatever heat energy you are supplying, it totally converts into work done by the gas. Are you able to understand? Whatever heat you are supplying, it is used only to move the... So temperature of the gas is not increasing, but you are supplying heat energy. Are you able to understand? Piston, it can move upwards, no? If piston moves upwards, it means work is done by the gas. By the gas, on the gas, last class we have studied. Are you able to understand, ma? Work done by the gas is there. And how gas is doing that work? By taking the total heat energy which we are supplying externally. Are you able to understand what is happening? Now in this condition, specific heat is infinite. So I can heat a gas such that specific heat is 0. I can heat a gas such that the specific heat is infinite. Similarly, I can heat a gas such that specific heat is minus infinite also. And those conditions we are not discussing. Are you able to understand, ma? So by doing all this, what I understand that gas can be heated such that it can have any specific heat. It doesn't have a fixed specific heat. Are you able to understand? Only solids and liquids, they have a fixed specific heat. Gases does not have a fixed specific heat. Okay. So therefore what I say, completed, ma? Okay. So therefore what I say is, as heated such that they can have any specific heat. Minus infinity to plus infinity. Any specific heat they can have.
Now what I am doing is I remove the lid of the tank. You cannot be here. Now if I heat, pressure will increase. As pressure increases, gas will increase. So pressure obviously increases. So this is keeping the gas at constant. So in two conditions I will say specific heat effect at constant volume first condition. Constant pressure is second. Now let us study it documentation. So this is called as CET. Specific heat is represented by S1, putting gas is represented by CDS. Now let us study each of them in
Okay. So first one is heating of a gas at constant volume. Try it. Okay, ma? Heating at constant volume. Okay. So we will use the first law of thermodynamics. What is the first law of thermodynamics? Okay. So this is a gas container. This is a piston. Okay. And this piston is fixed here. It is not movable. Fixed piston. Okay. Now we are supplying heat energy to this gas. Are you able to understand? So therefore, if I use the first law of thermodynamics, what is first law of thermodynamics? Q is equals to delta U plus delta W. Okay. So delta W is definitely 0, no ma? Work is not done on the gas also, work is not done by the gas also. Because piston is at rest position, gas is not doing work. Nobody is doing gas on the gas also. So both are 0. So therefore, this term will become 0. Work done is not there in this condition. Are you able to understand? Only if piston moves up and down, then only work done will be there. No? Piston is at rest position. So therefore, nobody is doing work on the gas. Okay. So therefore, it means that Q is equals to delta U. What do you understand by looking at this statement? Q is equal to delta U means what? That's it. So total heat energy which you supply, it is utilized for changing only internal energy of the gas. And if internal energy increases, what increases? Temperature increases. Clear, no? Therefore, what I say? Therefore, I say that total heat energy is used for what? Is used to rise the internal energy, of gas. Clear, no? And internal energy is nothing but temperature rises. That is the meaning of this. Okay. This is called as heating of a gas at constant volume. Is it clear, ma? Now, let us go for a specific heat condition. See, ma. So what is specific heat? S is equals to Q by N delta T, no, ma? This is the equation of specific heat, no? Molar specific heat. So therefore, in the condition of constant volume, S can be written as CV. CV is equals to Q by N delta T. So therefore, what is Q value? Q value is equals to N CV delta T. Okay. So take this value and substitute in the first equation. Therefore, what I write? Q is nothing but N CV delta T is equal to delta U. Clear, no? Therefore, I say change in internal energy is nothing but N CV delta T. This is a very, very important relation. Okay. So what is the equation for change in internal energy of the gas? It is nothing but N CV delta T. Okay. What is delta U? Delta U is nothing but a change in internal energy. Change in internal energy. Delta T means what? Change in temperature. Okay, ma? So therefore, one thing which I can say is delta U is definitely proportional to delta T. It means if temperature increases, internal energy of the gas also increases. Is it clear? So therefore, from the same relation also I can write U is equals to NCVT, no? Now can you say what is the meaning of this statement? Delta U is equals to NCV delta T. U is equals to NCVT means what? Anybody? Huh? U means what? Total internal energy. T means what? Temperature. Total temperature. Temperature of the gas. That's it. Clear, no? So therefore, this is a change in temperature, no? So I have to write a change in internal energy. This is temperature and this is total internal energy. So equation for a change in internal energy, this is the relation. Equation for total internal energy, this is the relation. NCV into T. Are you able to understand the difference? Okay. So therefore, U is called what? U is called as total internal energy. Okay. And T is called as temperature of the gas. It is not change in temperature, ma. It is what? It is just temperature of gas. Understood, no? ఈ ఈక్వేషన్స్ అన్నీ మీరు 5 సార్లు 6 సార్లు రాస్తే గుర్తుండవు. 10, 15, 20 సార్లు ప్రాక్టీస్ చేసేసి మైండ్లో ఇన్స్టాల్ అయిపోవాలి అవి. then solving of the problems will become very easy. Understood? First law of thermodynamics should be understood very, very carefully. Up to here it is clear, Nama? So therefore, this is heating of the gas at constant volume. So therefore, what we have studied here, at a constant volume, whatever heat energy you supply, it totally converts into internal energy of the gas. That's it. Is it clear? Okay. So next we study about heating of the gas at constant pressure. Okay, ma? Constant pressure. Now let us see. Therefore, this is a piston. Okay, ma? So these are the gas. Heating the gas. What happens to the temperature of the gas? Increases. If temperature increases, velocity of the gas molecules also will increase because velocity is dependent on temperature. In kinetic theory of gases, energy is half RT. For a single molecule, half kT of energy. That is what we have studied. So energy depends on temperature. Energy is what kind of energy? Kinetic energy. Kinetic energy depends always on temperature. Are you able to understand? So if you heat a gas, temperature, if velocity increases, they go and strike the force. Force increases, pressure also increases. It means when you start heating the gas, because they are moving very fast. Okay, ma? And because pressure is increasing, these gas molecules, they exert more force on the walls of the container. The piston is movable here and piston starts moving upwards. So piston is moving such that pressure always remains the same inside the walls of the container. Then this is called as pressure. Okay, ma? So consider this is a massless piston, means it doesn't have any mass. Therefore, pressure on the outside and pressure on the inside, always it should be equal because piston is a massless piston. Are you able to understand? So here what is the pressure? P atmosphere. Outside the piston, atmospheric pressure will be there, no? And inside the piston also, atmospheric pressure only should be present. Okay. And this is what kind of piston? This is a massless piston. Okay. Therefore, the piston moving upwards such that pressure always remains same inside the container, always atmospheric pressure. Are you able to understand? So this type of heating is called as heating the gas at constant pressure. So write down some data about this one, ma. Okay. So to Law of Thermodynamics. Is it 0? No, we are supplying heat energy, no? Delta U, is it 0? No, temperature is increasing, no? Work done, at least is it 0? Work done also is not 0. Okay? Because definitely gas is, its volume is increasing. So therefore what you say, the total heat energy which you supply, it will do two things. It will do two things. What are the two things it will do? First of all, it can rise. Okay, ma? So therefore, the heat which you supply, it can do. So it can rise internal energy. Similarly, it can do some work also. Are you able to understand, ma? Therefore, write down. Q is not 0. Delta U is not 0. Work done also it is not 0. Clear? Therefore, the heat supplied can do two things. First one, it can rise internal energy. Second one is work can be done. Okay. So only in the case of constant volume process, work done will be 0. But here work done is not 0. And heat supplied is also not 0. Change in internal energy also is not 0. Is it clear? Therefore, what I say, Q is equals to delta U plus delta W. Okay, ma? Now let us go for the concept of specific heat here. S is equals to Q by N delta T, no, ma? And we are heating the gas by using which method? Constant pressure method. So therefore, instead of S, I can write Cp. Cp is equals to Q by N delta T. So therefore, what is Q? Q is equals to Ncp delta T. Correct only, no? We are heating the gas at constant pressure only, no, ma? So Q is equal to Ncp delta T. Now take this value and substitute in the first equation. Okay. If I substitute in the first equation, let us see what we can write. Now we are doing a very, very important derivation, ma. So listen very, very carefully. So Q is equals to delta U plus delta W. Now listen, ma. Instead of Q, what I can write? Ncp delta T. Okay. And change in internal energy, already we have written, it is Ncv delta T, no? Change in internal energy is nothing but Ncv delta T. Plus work done can be written as P delta V, no? Because pressure is a constant, no, ma? But volume is changing, no? Oh? This is what kind of process? Constant pressure process. In last class we have studied equation for work done under two conditions, no? Work done when pressure is a constant. Work done when pressure is not a constant. Here pressure is a constant or not. So therefore equation of work done is P delta V. Is it clear? So ideal gas equation we have, no? What is ideal gas equation? So PV is equal to nRT. So therefore I can write P delta V is equal to nR delta T. Can I write? I can write, no? Change in volume is because of change in temperature. Pressure is not changing. Number of moles is not changing. R value also, it is not changing. So therefore instead of P delta V, I can write nR delta T. Okay, so substitute. So therefore Ncp delta T is equals to Ncv delta T plus nR delta T. What are the terms which can be cancelled, man? N delta T, N delta T, N delta T I can cancel. Okay. So therefore what are the values I have? I have Cp is equals to Cv plus R. R you can write Cp minus Cv is equal to R. This relation we call it as Mayer's relation. Understood now? Understood now how we are deriving? Right. These derivations you must understand and you must practice them many times, because everything is based on understanding of these equations only. Okay. So therefore I write this relation is called, what relation is called? Mayer's relation. Okay. Cp minus Cv is equal to R is called as Mayer's relation. Is it clear, ma? Cp means what? Specific heat of a gas when we are heating the gas at constant pressure. Cp. Okay, ma? And Cv means what? We are making volume of the gas constant and we are heating the gas and we are checking how much heat energy is required. That is called Cv. And relation between both of them is Cp minus Cv is equal to R, where R is called as universal gas constant, whose value is 8.31 in SI system and it is 1.98 in CGS system. Is it clear, ma? That's it. Okay. Now, let us study the relation between Cp and Cv to the degrees of freedom. Completed up to here? Okay. Now see. Oh. Okay. Cv in terms of degrees of freedom. Are you able to understand, ma? See, ma, change in internal energy, this is nothing but NCV delta T, no? Change in internal energy is nothing but NCV delta T. Okay. Now, what is meant by U? Total energy of the gas, total internal energy of the gas. Energy, internal energy, both are same. Clear, ma? Total energy of the gas is nothing but U. And total energy of the gas depends on what? Number of moles multiplied by degrees of freedom multiplied by half RT. Do you remember? Okay, ma? So half RT is the energy of 1 mole of gas. Half RT is the energy of 1 mole of gas molecules for each degree of freedom. How many degrees of freedom? F. F depends on whether it is a monoatomic gas, diatomic gas, or triatomic gas. All this we have studied previously, no? And how many moles of gas is present? N number of moles of gas is present. So this is the total internal energy of a gas. Similarly, but I want a delta U, no? Delta U, how can I write? Delta U depends on what? Only temperature. So therefore, N into F into half into R into delta T. That's all. No? So first equation, second equation, both of them, they are representing a change in internal energy only, no? So why don't you equate them? Okay. So if I equate them, what I will get? So therefore, NCV delta T is equals to N into F into half into R into delta T. Okay. Now what are the terms which can cancel? N delta T will get cancelled. So therefore, what is the equation of Cv? Fr divided by 2. Very, very, very important equation. Okay. So specific heat of a gas at a constant volume, in terms of degrees of freedom, you can write it is equal to Fr divided by 2. Is it clear? Make a note. Fr divided by 2. Okay. Now, similarly, I can calculate a Cv also, in terms of degrees of freedom. Cv already we have calculated. Cv also we can calculate, Cp also. What is the relation between Cp and Cv? Cp minus Cv is equal to R. So therefore, what is Cp value? Cp is nothing but R plus Cv. Okay. So therefore, Cp is equals to R plus Cv value is how much? Fr by 2. So Fr divided by 2. So therefore, Cp is equal to R. If I take common, then it is 1 plus F by 2. Okay, ma? So this is the equation for Cp of a gas. Are you able to understand? So how I have calculated Cp value in terms of degrees of freedom by using Mayer's relation. Cp minus Cv is equal to R. Are you able to understand, ma? So linked derivation, ma. Once you understand the basic concept, you can go on deriving all these concepts very, very easily. Okay? Okay. Now, we will write Cv and Cp values for monoatomic, diatomic and polyatomic gases. Clear, no? So, first of all, we will write Cv value for monoatomic gases. Then diatomic gases. And for polyatomic gases, non-linear. Polyatomic, or you can say triatomic also, both are same, but they should be non-linear. Okay, ma? If it is triatomic, it should be non-linear. Now, so for monoatomic gas, what is F value, ma? Number of degrees of freedom? 3, no? Number of degrees of freedom for monoatomic gas is 3. So substitute 3 in this equation, Fr divided by 2. So therefore, for monoatomic gas, CV value is how much? 3R divided by 2. Are you able to understand? These values you must remember them. Because in the questions, this data he will not give. Monoatomic gas, CP, CV values he will not give. You have to remember them. And which one is monoatomic, which one is diatomic, which one is triatomic, that also he will not give. You have to find out. Are you able to understand? For example, he says ozone, monoatomic, diatomic or triatomic? Triatomic. 3 oxygen atoms are present. Immediately you have to write its respective CV value and its respective CV value and its respective gamma value also, which we will discuss later. Okay. So CP, how much ma? Here also monoatomic gas, number of degrees of freedom are 3. So see how much if I substitute 3 here. So CP is equals to R multiplied by 1 plus 3 by 2. 1 plus 3 by 2 is 5R divided by 2. That's all. No? So for monoatomic gas, CV is 3R by 2, CP is 5R divided by 2. Now do the remaining calculations. Okay. So for diatomic gas, number of degrees of freedom are 5. Here also number of degrees of freedom are 5. Okay, ma? So therefore it is 5R divided by 2 and it is 7R divided by 2. Okay. Polyatomic as triatomic non-linear molecules, F value is how much? F value is 6. Okay, ma? So 6R by 2 is how much? 6R by 2 0 na? Oh, 3R. And CP value is 4R. Okay, ma? These values you must remember, ma. 3R by 2, 5R by 2. Okay? 5R by 2, 7R by 2. 3R, 4R. Is it clear? These values you must by heart them, and how we have derived them, everything should be in your brain. Okay? So let us keep the next side heading, adiabatic constant. Okay, ma? Okay, ma? So the next topic is adiabatic constant of a gas. So what is meant by adiabatic constant? It is called as gamma. Adiabatic constant is represented by gamma. So it is just the ratio of Cp divided by C. This ratio is called as adiabatic constant. Clear, ma? So for a particular gas, the ratio of Cp by Cv is nothing but gamma. So what is meant by Cp? Already we have written, ma, R into 1 plus F by 2 in terms of degrees of freedom. Okay. And the Cv value is how much? Fr divided by 2. Already we have derived all of them. So therefore, if you cancel this R and R, then what I will get? I will get 2 multiplied by 1 plus F by 2 divided by F. This is what I will get, no? So therefore, if I multiply everything by 2 and divide by F, so 2 plus F divided by F. So it is 2 by F plus 1. So therefore, what is gamma value, ma? Gamma value is 1 plus 2 by F. So this is the equal value of gamma in terms of adiabatic, in terms of degrees of freedom. Are you able to understand? So gamma is Cp by Cv. But in terms of degrees of freedom, it is 1 plus 2 by F. Okay. Now gamma value changes from monoatomic, diatomic and triatomic gases, ma, because F has different values in 3 types of gases. So therefore, let us calculate gamma value for monoatomic, diatomic and triatomic gases. Okay. So monoatomic gas gamma value is 1 plus 2 by 3. That's all, no? So 5 by 3. So for diatomic gas, okay, so gamma is equals to 1 plus 2 by 5, 7 by 5. Triatomic, non-linear or polyatomic gases, for them gamma value is 1 plus 2 by number of degrees of freedom are how many, ma? 6. Okay. So 8 by 6, it is 4 by 3. Okay. So these are the gamma values for monoatomic, diatomic and triatomic gases. Clear ma? Make a note. Okay ma? So next side heading is internal energy of gas in terms of adiabatic constant. Okay ma? So I want to derive an equation for internal energy of the gas in terms of adiabatic constant. What is meant by adiabatic constant? Already we have studied now. The ratio of Cp by Cv is called as adiabatic constant. Okay? Now see. See, we have a relation Cp minus Cv is equal to R, which is called as Mayer's relation. Okay? And also we have gamma is equal to Cp divided by Cv. So Cp can also be written as gamma into Cv. Can I write like this? వింటున్నారా కాన్సన్ట్రేషన్గా? ఇది ఏంటో సోడి చెప్తాను, నోట్స్ రాసుకుంటే చాలా అన్నట్టు వింటా ఉన్నారా? లేదు కదా? ఓకే. సో Cp is equals to gamma into Cv. So take this Cp and substitute here. So gamma Cv minus Cv is equal to R. So Cv if you take common, then it is equals to R divided by gamma minus 1. Clear number? So this is one relation to calculate a Cv in terms of adiabatic constant. This is the equation of what ma? Cv in terms of what? Adiabatic constant. Cv already we have calculated in terms of degrees of freedom, Fr divided by 2. That is in terms of degrees of freedom. This is the relation in terms of gamma value, adiabatic constant. Clear no? And we know that, okay ma, Cp minus Cv is equal to R. Okay? Or just you can write like this also. You can write Cp is equals to gamma into Cv no ma. So therefore Cp is equals to gamma multiplied by R divided by gamma minus 1. Okay? So this is the equation to calculate Cp. In terms of what? In terms of again degrees of freedom. Sorry, in terms of adiabatic constant. So this is the equation for Cv and this is the equation for Cp. R by gamma minus 1 and gamma into R by gamma minus 1 for Cp. Clear? Now let us study about internal energy of a gas. Okay? Actually what is our heading? What we are trying to do? We are trying to derive internal energy of gas in terms of adiabatic constant. Clear number? So therefore U is equals to NCV into T. Do you remember this one? Total internal energy of the gas, that is the product of N into Cv into T. Cv value already we have derived, no? So substitute here. So N multiplied by Cv value R by gamma minus 1 multiplied by T. Clear number? So therefore U is equals to nRT divided by gamma minus 1. So this is the equation to calculate total internal energy of the gas in terms of adiabatic constant. Okay? And from ideal gas equation, nRT is nothing but PV no ma. So PV divided by gamma minus 1 also you can write. Are you able to understand? From ideal gas equation, PV is equal to nRT, no? So instead of nRT, I can write PV also. Similarly, delta U, how I can write? Delta U can be written as nR delta T divided by gamma minus 1. I can write like this also. That's all, no? Change in internal energy is because of change in temperature. So nR delta T divided by gamma minus 1. I can write like this also. Is it clear? Okay, ma? Similarly, this also I can write it as P2 V2 minus P1 V1 divided by gamma minus 1. Are you able to understand? Because nR delta T, change in temperature means pressure also will change, volume also will change. So from ideal gas equation, P2 V2 minus P1 V1 divided by gamma minus 1. So these are the different equations to calculate internal energy of a gas in terms of adiabatic constant. Okay, ma? In terms of degrees of freedom already we have calculated, no? Now this is in terms of adiabatic constant. Clear? Make a note. Now see. So this is one point which you should remember, ma. Cp is always greater than Cv. Why? See, ma, this is heating the gas at constant volume, no? Sorry, constant pressure. Okay, ma? And this is heating of the gas at constant volume. Okay? So here the amount of heat energy which you supply, it will do two things. That's it, no? The amount of heat energy which you supply in this condition, that heat energy is divided for doing two things. First of all, it should rise some temperature, and then it should move the piston upwards also. Clear, no? So here, the rise in temperature will be very slow, no ma? Rise in temperature will be very slow, because total energy is not used for rising the temperature. Some of the energy is used for lifting the piston upwards also. But in this condition, total heat which you supply, it will be useful only for rising the temperature of the gas. So in this condition, temperature rises very fast. Are you able to understand, ma? So therefore, here I have to supply more amount of heat energy, no, to rise the temperature. But here if I spend less amount of energy, that will be enough. So therefore, now see here. So Q is equals to NCV delta T. Q is equals to NCP delta T. What is the CV and CP? They are nothing but a specific heat of a gas. Okay. So for same rise in temperature, for rising 1 degree Celsius, so temperature of this gas is also 30 degrees. Temperature of this gas is also 30 degrees. I want to raise this temperature from 30 to 31. This one also I want to rise from 30 to 31. Delta T is same number. Consider number of moles also, they are same. In which condition I have to supply more energy? In this condition I have to supply more energy. Why? Because total energy is not used for rising temperature. No, only some energy is used for rising temperature. So you have to supply more energy so that piston also moves upwards. But here you need to supply only less energy, because total energy is used for rising the temperature itself. So if Q is lesser, S is also lesser. So if Q is lesser, CV is lesser. Q is greater, CP is also greater. So CP is always greater than CV. And how much it is greater? R. It is greater by R. Because in Mayer's relation already we have studied, no ma? CP minus CV is equal to R. So R is always a positive value, 8.31. 8.31 joules per mole Kelvin. Are you able to understand? Joules per, that's it. So CP is greater than CV by how much value? It is greater than, it is greater by 8.31 when compared to CV. Why it is greater? It is understood, no ma? Because here the heat which you supply, it will do two things. So temperature rises very slowly, you have to supply more energy. But here total energy is used only for rising the temperature. So CP is always greater than CV. So right now. So at constant pressure, heat supplied is utilized in doing two things. One is rising temperature, and the second one is lifting the piston upwards or moving the piston upwards. Understood, Nama? But at a constant volume, okay, ma? Heat supplied is used only for rising temperature. Okay, ma? Therefore definitely CP is always greater than C. That's it. Okay. Sima. So this is a question, ma. So two identical cylinders with same number of moles. It means N values are same, number of moles are same. So and both are filled with the same gases, ma. So therefore their adiabatic constant is also same. It means same type of ideal gas. It is filled in both cylinders. Okay. So piston A is free and another piston is fixed here. It means we are taking two identical cylinders. So piston of one, it can move, and the second piston, it is a fixed piston. That is the difference. Okay. So same amount of heat is absorbed by each cylinder. It means the amount of heat energy which we are supplying, it is same. So here it is Q1, here it is Q2, Q1 and Q2 both are equal. Then in which cylinder temperature rise will be more? In which cylinder temperature rises by greater value? What is the answer? So this is A, Noma, and this is B. So definitely in B, rise of temperature will be larger. Why? Because total energy is utilized only for rising internal energy, no? So temperature rises by greater factor. But here the energy which you are doing, it will do two things. It will rise temperature also, it will rise the piston also. So energy is distributed. So rise of temperature will not be greater. So what is our first answer? First answer is temperature rise in cylinder B will be greater. That is our answer for first question. Okay, ma? Now second question is, if temperature rise in cylinder A is a T0, then what is the temperature rise in cylinder B? So in this condition, change in temperature is how much? It is T0 in cylinder A. Clear, nama? Then a change in temperature in cylinder B, this is how much that he is asking. Understood, nama? So for both cylinders, we are supplying same heat energy, no? So therefore, can I say that Q1 is equal to Q2, or you can write QA is equals to QB. I can write like this also. Are you able to understand? Now what is Q here? QA is nothing but heating the gas at constant pressure process. That is the meaning of this one, nama. So piston A is free means what? Piston A is free means as pressure rises, piston will move upwards. That is the meaning of that one, no? It means this is the example of heating the gas at constant pressure. Okay? And what is the equation to calculate heat energy supplied when gas is heated at constant pressure? So it is NCP delta T in cylinder A. That's all, nama. And in second cylinder, we are heating the gas at fixed volume. Piston is not movable, no? So fixed volume. So fixed volume means heat energy supplied, already we have written, it is NCV delta T of cylinder B. That's all. This is what we have written, nama. So change in temperature in A is how much? T0. So therefore you write down N multiplied by Cp multiplied by T0. This is equals to N multiplied by Cv multiplied by delta Tb. Number of moles are same, no? Clear, nama? Therefore delta Tb only he is asking, no? So delta Tb is equals to Cp by Cv multiplied by T0. And Cp by Cv is gamma value. So therefore delta Tb is equals to gamma multiplied by T0. This is my answer. Is it clear, no? That's all, very simple. So gamma value is always greater than 1, no? Okay, ma? What is gamma? Gamma is the ratio of Cp by Cv. And Cp is always greater than Cv. It means gamma value is always greater than 1. It means a change in temperature in second cylinder, it is always greater than T0. Understandable, no? Because here we are heating the gas at constant volume. Here rise in temperature should be greater. That's it. Okay, right. See, ma'am. So this is the next question. An ideal gas with adiabatic component exponent gamma is heated at constant pressure. So this is a constant pressure process. So it means internal energy also increases, pressure of the gas, what you call work will be done on the piston also. Both works will be done, no? So determine the fractions of heat absorbed in rising internal energy and work done. What is the meaning of this one? What is meant by Q, ma? Q is called heat absorbed, no? Or heat supplied to the system. Okay? And rising internal energy means delta U. Work done means delta W. That's all, no? So he is asking fractions. Fractions means what? First one which we are supposed to do is fraction of rise in internal energy divided by Q. This is called as fraction. Understood, no? Second fraction is work done divided by the total heat energy which is supplied. This is called fraction. So amount of work done to rise the internal energy, amount of energy spent in rising the internal energy to total energy. Amount of work done again divided by total energy, that is called fraction. Okay, ma? So write down. So delta U I can write it is equal to NCV delta T, no, ma? And Q can be written as, Q means total heat energy, NCP delta T. Constant pressure process only, no? In constant pressure process, Q is what? NCP delta T. And change in internal energy is nothing but NCV delta T. So change in temperature is same, number of this is also same. So delta U divided by Q is nothing but CV divided by CP, which is nothing but 1 by gamma. That's all. That is my answer. Nothing. Okay, ma? Now see. So delta W divided by delta Q. Delta W, how can I write? We know that Q is equals to delta U plus a delta W, no, ma? Therefore delta W is nothing but Q minus delta U. Okay, so take this delta W and substitute here. So Q minus delta U divided by Q, this is equals to 1 minus delta U divided by Q. So 1 minus delta U by Q already I have calculated now, 1 by gamma. That's all. This is my answer. Okay. So one answer is 1 by gamma, another answer is 1 minus 1 by gamma. That's it.